Ever wondered how the first galaxies ever formed look like? Was there a time you stopped and thought to yourself how the universe looks like 200 million years after the Big Bang? Well, we might just have the means to get a glimpse of the world outside of our own and the history and mystery that lies underneath this vast cosmos that we're in. Hello there, and welcome back to the Discover Space channel, where we explore space and the world beyond it. For this video, we will take a look at the latest images and updates sent by the largest, most powerful space telescope ever built, the James Webb Space Telescope. Be sure to subscribe if you haven't already, and let's get on it. As NASA's James Webb Space Telescope moves through the final phases of commissioning its science instruments, we have also begun working on technical operations of the observatory. While the telescope moves through space, it will constantly find distant stars and galaxies and point at them with extreme precision to acquire images and spectra. The Webb team recently completed the first test to track a moving object. The test verified that Webb could conduct moving target science. As we move forward through commissioning, we will test other objects moving at various speeds to verify that we can study objects with Webb that move throughout the solar system. Here it's about to get slightly technical, but I promise you, it's far more exciting than you think. First off, we'll look at Webb's coldest instrument, the Mid-Infrared Instrument, or MIRI. MIRI will allow us to study the universe in infrared light, which is invisible to human eyes, but can be detected by this special instrument. This image shows the Large Magellanic Cloud, a satellite image in the Milky Way, as seen in the MIRI test image. Spitzer's infrared array camera previously captured an image of this same target, allowing for a direct comparison of the two telescopes' abilities. Webb's MIRI image, for example, depicts interstellar gas in remarkable depth. Here, you can see the emission from polycyclic aromatic hydrocarbons, or molecules of carbon and hydrogen that play an important role in the thermal balance and chemistry of interstellar gas. When Webb is ready to undertake science observations, research like this with MIRI will aid astronomers in learning more about the formation of stars and protoplanetary systems. Now we take a look at the Webb telescope's image sharpness check. Engineering photos of sharply defined stars in each instrument's area of vision show that the telescope is perfectly aligned and focused. For this test, Webb looked at a tiny satellite galaxy of the Milky Way called the Large Magellanic Cloud, which provided a concentrated field of hundreds of thousands of stars over all of the observatory's sensors. The sizes and placements of the photos indicate the relative arrangement of each of Webb's instruments in the focal plane of the telescope, each aiming at a somewhat offset region of the sky from the others. Webb has three imaging sensors. First is the NIRCam, second is the NIRIS, and third is the MIRI. We also have NIRSpec, which is a spectrograph rather than imager, but can take images, such as the 1.1 micron image shown here, for calibrations and target acquisition. The dark spots shown in certain NIRSpec data are due to the micro-shutter array's architecture, which includes hundreds of thousands of adjustable shutters that may be opened or closed to select which light is delivered into the spectrograph. Finally, Webb's fine guidance sensor follows guide stars to precisely aim the observatory. Its two sensors are not typically utilized for scientific imaging, but they can take calibration images like the ones displayed here. As part of Webb's entire instrument calibration process, this image data is used not just to analyze image sharpness, but also to carefully detect and calibrate small image distortions and sensor alignments. Finally, let's take a look at the alignment process. The Webb crew is making progress with the observatory's mirror alignment. The first part of this procedure, known as segment image identification, has been accomplished, and the resulting image indicates that the team has manipulated each of Webb's 18 primary mirror segments to put 18 unfocused copies of a single star into a hexagonal shape. The alignment process was started with this image mosaic, which shows 18 randomly positioned copies of the same star. The crew repositioned the primary mirror segments to arrange the dots of starlight into a hexagonal picture array to complete the first stage of alignment. The relevant mirror section that captured each dot of starlight is labeled. Webb's 18 primary mirror segments and secondary mirror were further aligned using precise motions ordered from the ground in this hexagonal image array obtained by the NIRCam during the segment alignment phase. Individual segment images are shifted to the center of the field during this phase of alignment, known as image stacking, to form one cohesive image instead of 18. All 18 segments are stacked up on top of each other in this image. The image will get much crisper after further alignment processes. Each of the major minor segments has been adjusted to provide one unified image of the same star using only the NIRCam. At this stage of Webb's mirror alignment, known as fine facing, the star 2 mass J1-755-4042 plus 655-1277 was photographed with a red filter to improve visual contrast. Every optical parameter that has been verified and tested is performing at or above expectations at this critical stage in the commissioning of Webb's optical telescope element. Webb's optical path also had no critical concerns or quantifiable contaminants or blockages, according to the team. The observatory has no problems gathering light from distant objects and delivering it to its instruments. Despite the fact that Webb's first-of-its-kind optical system is still months away from being delivered, reaching this milestone implies that the team is sure that Webb's optical system is performing as well as it can. The first in-focus image from one of JWST's cameras is extremely exciting, as it promises new discoveries about distant galaxies. This image is sharper and more focused than any previous infrared images in this region, taken by the Spitzer and WISE telescopes. With the James Webb Space Telescope's exceptional resolution, we can see previously hidden details in these galaxies. This provided us with an opportunity to learn more about their formation and evolution. Well, that's it for this video. Please be sure to tune in for future updates on the exciting stuffs that the James Webb Space Telescope has in for us this summer of 2022. We expect to see much more high-quality images of the distant galaxies. We shall see you then.